Okay, so we want to talk a little bit about equilibrium. We just watched this video, Fuse School Equilibrium video. Go ahead and watch it if you want. Looks like this right here. Recommend it. It's a good. Oh, that's not it. Where to go? Right here.
In this lesson,
yeah, right there. So, dynamic equilibrium by the Fuse School. It's a good one to look at. Okay, so let's talk about dynamic equilibrium. As I mentioned before, and as I mentioned in the video, dynamic equilibrium, dynamic means movement, okay? It means there is movement happening. Even though a system at equilibrium seems to be stationary or not moving, the fact is that there are things moving underneath the surface in small microscopic ways that you can't really see. So, when a system is at dynamic equilibrium, this means that the reactants are creating products at the same rate as the products are turning back to reactants. All right, so this has to happen in a reversible reaction. Not all reactions are reversible, but in a reversible reaction, equilibrium can be attained. So if we have something like this, A plus B produces C plus D, the reversible, if it's reversible, you'll see a double-sided arrow like this. Okay? Lots of times it'll be an arrow with, it'll actually have two like that as well. But arrows going both ways. So that in the forward direction, A plus B are the reactants, A and B. In the reverse direction, C and D are the reactants. Okay? So A plus B moving to C plus D, and then C plus D moving to A plus B. Okay, reversible. If this is happening at the same rate, that means the rate of the forward reaction is equal to the rate of the reverse reaction, then we have dynamic chemical equilibrium. Okay? So again, there's no measurable change, even though things are changing constantly at the microscopic level. So if you think about an example would be a saturated glass of iced tea. So think of a really sweet, really strong glass of iced tea, okay? It's super strong. As a matter of fact, it's so strong that you can't dissolve any more crystals in there. And what you would actually see, it probably are some undissolved crystals at the bottom of the glass, right? You know if it's super sweet, there's stuff at the bottom that cannot, no matter how much you stir it, cannot be dissolved in. You know that it is saturated, okay? There's as much in there as can possibly physically dissolve in there. So it might look like nothing's happening, but what's happening at a microscopic level is that the particles, the sort of the sugar iced tea particles, are dissolving. They're breaking up and going into solution at the same time that two of these little dissolved particles are actually coming together to form the larger sugar crystal again. So the dissolving and the recombining are happening at the same time at the same rate. And so if you think about this glass of iced tea, all right, at the bottom of the glass, here's your iced tea. Let's make it brown. Okay. So there's little bits of undissolved iced tea in there. And even though if you stare at it, you can't see anything happening, what's happening is these little crystal particles are coming back into solution and they're getting kind of lost in there, dissolved, and you can't even see them. But at the same time that that's happening, and it has to happen at the same time and at the same rate, if it's in equilibrium, that two other particles are kind of bumping into each other and coalescing and returning back to the bottom. Okay? So it's kind of like, think about this. Think about a room full of people, okay? And here's the door, and all you can see is this mass of people, okay? They're all stick people, and they're all standing in there, but there's literally no room for anybody else. If another stick person comes in, and they're walking in here, and they're coming, and they shove themselves into the room like that, really what has to happen, if it's completely full, when they push themselves in, somebody has to get pushed out, right? And so either someone goes out the window, which would be very tragic, or someone squeezes out the door at the same time they come in. Can you envision that? And no, we're not going to test that. We're not going to try and get everyone in the school into this room here. Although that would be kind of interesting. We're doing a science experiment. We're opening up all the windows, and we're opening the door, and we're just packing this room full to the very top, and then we're going to add one more person and see what happens. Yeah, no, it wouldn't be good. Mr. Maxwell would lose his job. You guys would get hurt. There would be a whole bunch of unpleasant things result from that. Okay. So you get that, though? Okay. Oh, there's the phone. The phone is ringing. All right. So I will. Okay. So we just kind of wrote this. I will pause here, and you can jot down this right now, and I'll talk about it in a minute. All right. Just talked about this, and for this one right here, for this reaction, okay, kind of mentioned this as well. A plus B produces C plus D. The forward rate, from what we've just learned about the rate law stuff, right? The forward rate equals some rate constant for the forward reaction times the concentration of A and the concentration of B. Now, we're assuming that this is a one-step, single-step reaction. So in the rate law stuff that we've been working with and that you've had those charts, right? And, right, like where is it here? Just if I can grab it, maybe not here. Anyways, the charts where you look at, okay, so A is doubled in concentration, what happens to the rate, right? So in those questions, there's multiple steps. There's rate determining steps and everything, and there's multiple steps. And so some of the reactants don't affect the rate directly, and some do. But in these ones, we're just talking about kind of single step, simple reactions, okay? So we can assume that both A and B affect the reaction rate. So we're going to simplify this a little bit. All right. So you can assume for these ones that the rate equation looks like this, and we'll talk more about this as we move through this. But the reverse rate, okay, would be the constant, whatever that would be, for the reverse reaction when C plus D, right, produces A plus B. And this is how you would sort of explain that, right? So at this point, if the rates are equal, then we have this situation. All right? We have this situation. The forward rate equals the reverse rate. Now, if we manipulate this equation, because both sides are equal, we can divide by, both sides by the same thing and all that. If we divide both sides by concentration of A times concentration of B, and also divide both sides by K of R, we get this right here. Okay? That is the ratio of the constant for the forward rate over the constant for the reverse rate is equal to this. And what we're doing is we're getting closer and closer to another kind of constant, another kind of reaction rate constant. And this reaction rate constant is not just a forward reaction rate constant, or just a reverse, but it's the ratio of the two. And it's something special called the equilibrium constant. And so that's what we're moving towards here right now. So we'll just move this screen down here a little bit. And so this right here, okay, this is what we just wrote here. This forward rate constant over the reverse rate constant is a new constant, as I just mentioned, the equilibrium constant. So the KEQ is actually this KF over KR. And so what we see is the equilibrium constant is determined by the concentrations of the products and the reactants in this way. Okay, so now we move down to here. And this is very, very important. You have to write this down. This is super, super important. Well, you should be jotting down a few more things like this and all that sort of stuff and what we did before. But the equilibrium constant, okay, so again, we're assuming that these are simple, straightforward reactions both in the forward and reverse direction. And so that means that we don't have to look at lab data to figure out what the exponents are and how they're affecting the rate. We can assume that whatever the coefficients are, okay, in these chemical equations, those are going to be the exponents. All right? So notice, we have the KEQ equals the concentration of the product of the concentration of the products, so concentration of P times Q, and this, whatever this coefficient is on P, is the exponent. Okay? And R is the exponent there. So this equation is built like this. This is the KEQ. So let me just zoom in a little bit there. If I can get that in. All right, everyone see that? Yeah, so the one addition that I made here, this is a reversible reaction, so it really should have a double arrow there that wasn't originally on there. Okay, so you read this. I remember this came up in that chapter 22 pre-quiz, right? And it was if the equilibrium constant is greater than 1 or large, what does that tell you about the products or the reactants at equilibrium? So here's the explanation, and maybe you can see a little bit better why now. If the KEQ, and remember the KEQ is just a constant, okay? It's a number. Sometimes it's really small, sometimes it's really large. If it's large, though, that is greater than 1, and usually large is not just 1.1. It's usually quite a bit larger, 10, 50, 100, something like that. Then what that means is that the product of the concentrations of, in this case, P and Q, which are the products, so the product concentrations are much greater at equilibrium. Okay, so think about this in a math way, right? If we have a large number here, that means that the numerator has to be much larger than the denominator. And if this is much larger, it comes from the product of the concentrations. So if KEQ is large, that means these concentrations are much higher. That means the products are favored. Okay? Now what does favored mean? Well, equilibrium does not mean that we have equal amounts of reactants and products. It does not. It only means that the rate at which they are converting to the other is the same. So if I could let's just say we have H2 plus I2. That was in the video. And this is another way that you'll see, okay, me and others draw the equilibrium arrows, kind of a half arrow in one way and a half arrow the other way. You'll see that a lot in university and whatever. That's equilibrium. With 2HI, let's say. So if you think about this, if we start off with a whole bunch of H and I, and really we start off with no HI at the beginning, what happens is as this reaction occurs, then what happens is the amount of H2 and I2 decrease, and the amount of HI starts to increase. If equilibrium is reached as this moves along, and then boom, we have equilibrium right here, that means that this forward reaction and the reverse reaction are happening at the exact same rate. But it does not mean that the amounts of each have to be the same. Okay? So in this case, if the KEQ is greater than 1, that means that there are more products. More moles of products. Okay? The products are favored. Right? Now, if the same thing happened and at a given temperature or whatever, that the reaction started and it came to equilibrium very quickly, and let's say the H2 only went down to there. So there's this much H2 left and this much I2 left, and there's only a small amount of 2HI. If this was at equilibrium now, because there's so many more reactants, if you go back to our equation, that means that this number is now very large, right? So that would be very small amount here, very large amount here, and that turns out to be a small number, right? A number that is a number that's like less than 1. Okay? And so you're going to have numbers that are greater than 1 or between 0 and 1, because it can't be negative. So it's going to be KEQ. If it's less than 1, between 0 and 1, that's what this would be. The reactants are favored. At equilibrium, you have more reactant. And that's what this note above just says right here. If KEQ is small, then reactants are favored. and this less than 1 should be clarified. The KEQ is between 0 and 1. So small that way. Okay, do you have any questions? No? Okay, I'll give you some equations, and we'll just practice writing the KEQ expression. So again, these are KEQ expressions, so we'll do that. All right, so here's an example. H2O2 plus 2HI is in equilibrium with 2H2O plus I2. Okay, so if this is a situation and you see that this is at equilibrium, then you can write an equilibrium expression. Okay, so let's get some practice doing that. Now remember, the KEQ is comprised of the product of the product concentrations and divided by the product of the reactant concentrations. Okay, so that's kind of the pattern we're looking for. And again, we have to pay close attention to what the coefficients are. Okay, so we're going to fill in up here. This is going to be H2O, the concentration of H2O, times the concentration of I2. What I also need to realize is that this number 2 right here means what? What do I do with that number 2? Sorry? That's right. So there's an exponent of 2 here on this H2O. Okay? All right. So that's good. That's great. Now, so remember, we always start with the products up top. Products are up top. And then on the bottom are the reactants. Now, the reason why, and I know it's a reversible reaction, so you might be thinking, what does it matter which one we put up on top and which one we put on the bottom? Well, it does matter because if you switch these around, and you can, the KEQ will be opposite. It will be a reciprocal. Okay? If you are looking at this the opposite way, and you put, the reactants on top and the products on the bottom, then the KEQ is going to be different, right? So for the KEQ, for this expression, the way it's written, we always start with the products, the things on the right, chemicals on the right. Okay? So reactants here, we're going to have H2O2, and we're going to have HI. Now what do I do? So this is a power of 1, right? We'll leave that, and this coefficient means I need to have that expression there. Okay? So there's the KEQ expression. Right there. Does that look good? Understand? So once again, make sure that you remember to put the exponents. You do not have to place the 1. You don't have to show that. Make sure these are not rounded brackets. They're square brackets representing concentration. Okay? And concentration, you know what concentration is measured in? Sorry? Okay, capital M, it's moles per liter. So concentration is moles per liter, always. Not grams per liter, not grams per whatever. It's moles per liter. So capital M, you say that molar. So if it was 2 capital M, you'd say 2 molar. And that means moles of substance divided by liters of substance. Okay? All right, any questions? Okay, so here's an example too where this asks you to actually determine the value of the KEQ. Now what you're given is a few things. You're given an equation, so that's great here, the equation. You're also given a temperature. Now why would you be given a temperature? Well, you don't have to include the temperature in any of your calculations, but what you have to understand is that the KEQ will change if the temperature changes. Okay? Because remember, temperature has an effect on reaction rate. It doesn't have an effect on the rate law itself, but it does change the value of K. So if I'm asking you for a value of K, that value of K is only valid at the temperature where the data is taken from. Okay? So you do not have to include 24 in any of your calculations. All right, but it is important. Now, if each concentration is 2.3 molar, and this would be, of course, at equilibrium. Now, equilibrium, I don't know if I've mentioned this before, but I abbreviate equilibrium a little bit of a different way than you've probably seen before. This comes back from my university days. EQM with a little exponent of B there. I don't know, that's just the way my One of my profs did it, and it was just easy, and I got the hang of doing that. So you might see this, that means equilibrium, because it's not a word you want to write 17 times in an hour, right? So equilibrium. All right, so what we need to do is we need to find the KEQ expression, and then we need to input the values appropriately and then calculate. So first of all, the KEQ expression. So if we did that, let's do this in blue. The KEQ expression would look like this. Well, you tell me, what do I write here on top? What goes on the top, the numerator here? Concentration of SO3, yeah. Concentration. Now remember, you don't put the 2 in there or anything. You don't put a 2 up front. Where does the 2 go? As the exponent. Divided by concentration of SO2 to the power of 2 times O2 to the power of just 1. Okay? So you put little concentration brackets around all of these, and this goes up as an exponent. Right? That's basically what you do. Okay. So now we're given the concentration of each. So this KEQ is going to come from this, 2.3. Now you can dump the square brackets once you fill a value in, because the concentration of 2.3 doesn't make sense. 2.3 is the concentration, so you can dump the square brackets. All right, and over here again, 2.3 times 2.3. So if that is the case, then you simply just evaluate that, and of course that's going to divide out with that. So it's going to be 1 over 2.3, which, what is that? Let's see, as a value there. 0.4348 looks good. Yeah, 0.4348. And now the units, we haven't talked about units for KEQ. Generally, what do we do for units for our constants? What did we do? What did we do with the units for the constants there? The constants can have depending on all of the units that are involved. They may have really strange units, just a combination of whatever's necessary for. So there's not a given unit for KEQ, so you don't have to write a unit there. So the KEQ is just 0.4348. Okay. So does this KEQ, being that it's between 0 and 1, would you think that the products are favored or the reactants are favored? What would you guess there? The reactants, right? Because it's less than 1. Okay. So at equilibrium, you're still going to have more SO2 and O2 than you will have of SO3. Okay. Any questions? Okay, let's do one more example. Okay, so it says at a given temperature, it doesn't matter what the temperature is, but just we're talking about this given temperature here. This KEQ is 1.88 times 10 to the negative 3. So that is that means that there's going to be more reactants or reactant than products when it reaches equilibrium. It's just a small number. The concentrations of each reactant at equilibrium are going to be this, 3.3 times 10 to the negative 5. Find the concentration of the products. That should be products. Okay? Concentration of the products. In this case, the products would be H2 and I2. Okay? So, like the same thing with all of these, you start off with your KEQ expression. Okay? We need to write our KEQ expression. And then we're going to solve for what we're missing. So the KEQ expression is going to look like what? Concentration of H2 on top to the power of 1. Now you got to make sure this is balanced, I suppose. Hey, I'm assuming that you know this is balanced. If it's an unbalanced chemical equation, you have to balance it first. That's very important. Times the concentration of I2. Divided by the concentration of HI squared because of the 2. Okay? Does it look good? Question?
Sorry, I think I just got too mixed up.
Okay.
Products on product?
Because what, sorry?
Sorry, the product is on
No, products are on the top always.
Oh, and
Yeah,
then it's just going up.
Yeah, products are on the top. Okay. All right. So the concentrations of each reactant. Now that's going to be just this HI is 3.3 times 10 to the negative 5. All right. So the KEQ is 1.88 times 10 to the negative 3. We can start filling in values here. H2 and I2 are unknown, right? They're unknown. So notice that it's a 1-to-1 ratio here. So as HI breaks up, the same amount of H2 and I2 are created. So they both can be just X are unknown that we're able to solve for. So you would put X here and X there. Okay. There will be other cases where these are not the same. We'll talk about those later. But you want to put your unknown in there. So this is 3.3 times 10 to the negative 5. And of course, don't forget about the squared. All right? We good so far? Okay. So now it's easy. This is baby stuff, right? Solving for x. This is actually x squared, right? And we want to, you can evaluate this. So let's do one more step here before we get too far gone. So that's x squared. What's 3.3 times 10 to the negative 5 squared? You can figure that out in your calculator. 10 to the negative 5 squared. Is this what you got? 1.225 times 10 to the negative 9. Negative 5 squared. Oh, I did 3.5 there. I just noticed. 3.3. That's all right. Exponent negative 5. And then we'll square that. Is that what you got? 1.089? 1.089 times 10 to the negative 9. Okay. And of course, we want to multiply these two together, right? So let's multiply 1.089 10 to the negative 9 times 1.88 times 10 to the negative 3. Make sure you use your scientific notation button. Okay. Multiply those together, you get this as a number. So that's 2.047 times 10 to the negative 12 equals x squared. And finally, to get x all by itself, you take the square root and, oh, where's my cursor here? And we will square root the answer. And we get 1.43 times 10 to the negative 6. So you are going to need to use your calculator a bit. And notice that we have two different numbers here with significant figures, right? So if you were wondering how many decimal places you should take your answer to, you look in the question. We have two sig figs here, so this should be 1.4 times 10 to the negative 6. And what is that going to be for a unit? What do we have here? X is a what? X is a concentration. Okay. So what is this going to be? Yeah. Did you have a question? Yeah.
So we don't put plus or minus.
Okay, good question. Yeah, when you take the square root, you're not going to put plus or minus. No, not in this, because it's just like in math when we're talking about distance or something. Don't worry, not a negative distance. When you're talking about a concentration, a negative concentration really doesn't mean anything. So just take the positive square root. Yeah, good point. I actually thought of that early in the question. I was going to maybe bring that up, but glad you reminded me. Okay, any other questions there? Remember, X was the concentration of one of these, and so the concentration of the products. So in your final sentence here, you would simply write this. The concentration of H2 is 1.4 times 10 to the negative 6. And of course, the concentration of I2 is the same. Molar. Okay? And there would be your answers. Be clear with your answers like that, okay? Don't just put X. Don't leave it like this. Okay? Not acceptable. because X was just a tool for you to find a value in your question. Now you have to convert that and communicate with me that you know what that X represents. Because X is not always going to be the answer in these problems. You're going to have to use X to plug that back into the equation or to the question to find out the value. Okay, so that's equilibrium. Those are the 3 different types of calculations and things that you're going to have to do with equilibrium. Any questions? Okay, so in the Merrill chemistry textbook there, page 562, you can do 10 to 15. That's this textbook right here.